Okay, welcome back. In the second half of the lecture we will talk about contemporary RISC architectures. So for a long time now, RISC and CISC have been the two sides of the coin of architectural design, representing two different design philosophies. In a CISC architecture like x86, you see there's this tendency to pile in as many features as you can. You're adding new features all the time, more niche instructions for particular applications, but at the same time you're maintaining this back compatibility with all the stuff that was added before. And the result of that is you now have this enormous instruction set in x86 with 3,000 instructions spanning a 5-volume set of books. Now RISC is the other side of this debate, and it takes the opposite stance. RISC says you should try and reduce the number of instructions and only have instructions that you really need, but then work really hard to implement them as efficiently as possible. So many CISC instructions never get used, or they're very rarely used. So even the compiler writers don't always know that they exist, or are unable to make good use of them. Whereas in a RISC architecture, you just want to present this lean and mean, stripped down instruction set. You make it as simple and reduced as possible, and then you, as an architect, you focus on making it go really fast. And as a compiler writer, you focus on making the best use of the available instructions. So RISC used to be a controversial idea in architecture. It came from academia. It was laughed at by industry. So you hopefully have a good idea now of how x86 evolved with this very commercial industrial focus. Yeah? And coming up against that from academia is going to be very difficult. So more recently, RISC has taken hold, especially in mobile devices, but increasingly on the desktop, even in cloud servers, and seems to be growing in terms of market share. So RISC design has always been linked to this idea of measurement. So we talked about the metrics, performance measurement at the start of the lecture. One way to manage your time as an architect is to continually measure the performance of your system and figure out where are the bottlenecks and what should we optimize, what should we focus on, and ideally what can we get rid of. In both in hardware and in software in computing, it can be as important to get rid of stuff as to create new stuff. Yeah, it's always a temptation to go on inventing more things because you feel like you're doing stuff, but throwing stuff out can be just as useful. And so when you read the RISC literature, these figures are from Hennessy and Patterson's book. So Hennessy and Patterson are the inventors of RISC. They won the Turing Award for it. And their book is full of figures like this, where they go out and they measure performance of things. They run a whole bunch of programs from the real world on a bunch of CPUs, and then they measure what are the CPUs actually doing, what are they actually spending their time on. So for example, in this figure, they're saying what kinds of operands are actually being used. Are they immediate operands? Are they addresses? Are they indirections? And they're measuring, look, this is how many data transfers and how many ALU operations are operating in immediate mode. You know, they're going to look at these numbers and they're going to use them to guide the design of the architecture, to optimize it for the things that are actually getting used. So here's another example. Here we're studying different addressing modes. Okay, so different types of indirection for different tasks. So this is a tech task. Tech or LaTeX is the typesetting not word processing. Yeah, typesetting system used in academic writing. SPICE is a electronic circuit simulator task. GCC is a compiler task. But they're saying in all these different kinds of tasks, what are the ratios of different things actually getting used? And therefore, should we include this type of addressing in our architecture or not? And so through decades of careful study and measurement of those performance metrics, the risk community's come up with a lean and mean core of operations that you really need in the CPU, and they're going to try and get rid of everything else. So completely opposing design from the CISC philosophy of just pile everything on top of everything else. So risk tends to dominate in terms of mobile devices. A feature of risk is because the designs are simple and lean and mean, they tend to use low power, and that makes them a really good fit for devices that have to be powered by a battery that you carry around in your pocket, because you get a longer battery life. You tend to find the stacks, as with everything in architecture, that they're structured at various levels. The core of any modern architecture is its instruction set. Often the instruction set architecture is just referred to as the architecture. Yeah? And the instruction set or the architecture means the definition of all the available instructions. It's the user-facing interface to the system. So there are two major interesting RISC architectures out there. There are others as well. Probably if you have a phone in your pocket, it is running the ARM architecture. This is a proprietary closed architecture designed in Cambridge by ARM, the company. And the new kid on the block is called RISC-V. And RISC-V is different because it is an open source architecture. That means it is developed by the entire community. Anyone is free to contribute to the design, and anyone is free to implement the design. So the last few years have seen a boom, pun intended, in RISC-V devices. So does anyone own a RISC-V device yet? No? You probably will soon. Okay, this is the challenger for taking over the RISC marketplace. Now, distinct from the design of the instruction set architecture is the work of actually implementing that architecture as a piece of digital logic, and that's what's traditionally called computer organization as opposed to computer architecture. So this is very different in the two stacks. Okay, in the ARM instruction set, there's only one company that is allowed to make instantiations of that architecture, and that is ARM itself. Okay, ARM does not allow anyone else to implement that instruction set, and so again, the internals of this are kept very secret, and therefore we can't really teach you anything about them because they're not public in the way that RISC-V is. But you'll see that the company ARM is doing two distinct activities. It's defining the instruction set, and it is also making digital logic implementations of that set. Whereas in RISC-V community, it's very different. Because the instruction set is open, that means anyone can come and implement the instruction set in their own digital logic design. So that can even include you. Okay, it's very possible now to run student projects, second year group projects, third year individual projects, where you actually build a CPU. And RISC-V is the go-to architecture for those kinds of projects now, because it's open. You're actually allowed to make an implementation of it, and it's become very, very doable just in the last few years. So many people are creating instantiations of RISC-V. Those include instantiations that are themselves open source. So Rocket and Boom, for example, are two. They're not quite made in Logisim. They're made in things a bit like Logisim, not so different from what you guys have done. But the source code for these designs is put up on GitHub, and anyone, including you, can go and download them and use them and manufacture them or modify them or do almost whatever you like with them. So these range from very simple, straightforward implementations that do everything like in a textbook, all the way up to very complex implementations like Boom. So Boom is the Berkeley out-of-order machine, and that's making the thing go as fast as possible, not by increasing the clock speed, but by using lots of extra digital logic to do out-of-order execution, which you remember is an advanced form of pipelining where many different instructions can be getting processed all at the same time, yeah, according to the dependency diagram of the program. But you'll also find commercial closed source instantiations, and some companies try and compete against the open source community by doing what they think is faster or better or more secure. And it's a very open market to see who can make the best instantiation. So ARM is going to have a lot of difficulty competing with this, right? ARM is one company trying to implement its own instruction set, whereas RISC-V is an open instruction set, and you've now got many companies and organizations all competing very tightly against one another to make the most efficient implementations that they possibly can. So once you have an implementation, once you have some digital logic, you then put it on a chip and you build that chip into a device. You do computer design. So typically these things are getting put in mobile devices like your phones and other digital gadgets. Increasingly they're finding their way onto more normal form factor computers, so that there are desktop versions. So ARM chips are now found in Apple computers, for example. They used to be found in Acorn computers back in the day. Okay, ARM used to stand for Acorn RISC Machines. It changed its name to Advanced RISC Machines, and then just to ARM. Whereas in RISC-V world, we're seeing companies like Sci5 has been making basically competitors to Arduino and Raspberry Pi, small single board computers with these RISC-V chips. And increasingly, they're getting bigger and bigger and more feasible for using as your daily desktop driver. Low risk is an especially interesting form of this because they are trying to build an entirely open source hardware computer. So that means not just the CPU design is open source through the stack, but the entire computer design. That means that the memory, all the I/O, the bus, everything is put upon GitHub, I think, and can be downloaded and contributed to. Low Risk is based in Cambridge. It's a well-funded organisation. It's an excellent place for you guys to go and work when you graduate if you are interested in computer architecture. They're doing some of the most exciting architectural work in the world at the moment. And it's just about commutable from here in Lincoln, if you don't mind a little drive down the A1 every day. So if we go up the stack, we can then look at organizations that are users of RISC instruction sets. And primarily these are operating systems. Okay, so you'll study operating systems next semester in a lot more detail. But roughly the operating system is a piece of software that runs on top of a particular architecture, and it provides a higher level abstraction for end user programmers to go through. So you're probably all familiar with some of these, maybe running on your phone. So you might be running Android on your phone, yeah? If you don't like being spied on by Google, you might prefer Replicon or Lineage. These are forks of Androids that have removed the Google spyware. So you just have the pure open source core of Android. Lineage is the one that actually works. Replicon is the extreme free software version that removes absolutely everything that is ethically problematic, but probably doesn't do very much on your phone as a result. You might have come across Raspbian if you're running Raspberry Pi. So Raspberry Pi is based on this ARM stack. Raspbian is a version of Debian, customized and specialized for this particular stack. Anyone heard of RISCOS? RISCOS was the original Acorn operating system from the early 1990s when the ARM1 chip was created. Acorn computers, the same people who did the BBC Micro. They made these wonderful 32-bit machines called the Acorn Archimedes at a time when the rest of the world was on 16-bit PCs. And RISCOS is an operating system designed to run on that original ARM1 architecture on the Acorn Archimedes, and it was hand-coded in ARM assembly to run very, very fast. And for its time, it was very impressive and way ahead of what everyone else was doing. It sat around doing nothing for a couple of decades until people noticed you can now go and run it on your Raspberry Pi, because your Pi is still back compatible with the ARM1 architecture. And because it was so carefully hand optimized to run on early 1990s machines, it now runs blindingly fast on a modern ARM device like a Raspberry Pi. So probably this is the fastest operating system in the world now, if you want blindingly responsive OS. Though less fully featured in terms of modern stuff than some of these alternatives. So you can kind of get an idea of the RISC community just by looking visually at these logos. Yeah, when you look at the x86 stuff, it just looks like an industrial, commercial, for-profit thing, whereas RISC World tends to feel a bit more friendly and a bit more community-driven. There's just kind of there's more colours in the logos and more friendly shapes and cartoon characters. That gives you an idea of what RISC World tends to feel like. So let's look at some details of a particular RISC instruction set then. This is RISC-V. Again, this is open source. That means we are allowed to talk about it and to study it. It's designed by some of the original RISC creators, led by David Patterson of Hennessy and Patterson. It's open source, but that doesn't mean it isn't well funded, so it gets cash from major computer companies like Google, AMD, Microsoft. There's one major RISC organization is obviously missing from this list, because RISC-V is competing directly against its products. And so all the people who don't like that company put in money to make the open source alternative. And RISC-V, because it's been designed from scratch, it's much cleaner than x86. Well, partly because it's from scratch and partly because it's inherently RISC, and the whole point of RISC is to be clean and mean. But you find all these quirks that you see in x86 are missing from RISC-V. Everything is very much the way that it should be and the way that a textbook would tell you how to design it. So RISC-V is technically a family of instruction set architectures rather than a particular one. So that includes versions that are 32, 64, and 128-bit. Yeah. So these guys are getting ready for the next era of architecture, the 128-bit era, when you have whole CPUs running on 128 bits. And here's some example instructions in RISC-V. So look, load and store. So just abbreviated by L and S, okay, which is really lean and mean. It's taken us about 50 years of architecture to get our assembly instructions down to single letters. Yeah, traditionally they're 3 letters long, but now we just have L and S for load and store. And if you want to do a load, you just say, where's it coming from, where's it going? That's the destination register, that's the address, that's the source register going out to an address. If you want to do arithmetic, it's very clearly structured, so you have 3 operands. You say these are the 2 inputs, that's the output. So take the numbers in register A and register B and store them in the destination register. Or you can do the indirect version. Notice, because it's RISC, we separate arithmetic from memory access. So when you do load and store, that's just load and store. When you do arithmetic, it is just between registers. You can't do arithmetic on data that's in memory. You have to load it into the CPU first. Whereas in CISC architectures, they tend to combine all that process together into a single, complicated, complex instruction. Here's some examples of branching. So notice there's no compare instruction. They put it all just in a single instruction. For example, this says branch if equal. If register 1 is equal to register 2, then go and set the program counter to what's provided in the third operand. Or you can branch if not equal. Here's how you do a subroutine. So in RISC-V, a subroutine is called a jump and link. A jump and link means you're going to jump to where the subroutine is. You're going to link the location that you came from. You're going to store that somewhere, usually on a stack, so that you can get back to it. And that's pretty much it. that's the set of everyday instructions that you tend to use. There's usually 32 integer registers, and they're just called register 0 up to register 31, rather than having these complicated names that you see in x86 architecture that have evolved over time. And then everything else in RISC-V is optional. It's designed as a family of architectures because you might want to instantiate RISC-V on a little tiny embedded system to control your coffee making machine, or you might want to instantiate it on a large server to put in your cloud compute center. And so RISC-V is designed to have that core of instructions, but then a set of optional extensions, and you can manufacture a RISC chip with whichever of these extensions you actually need. So even the basic integer arithmetic is optional, right? That there are some cases in embedded systems where you don't need arithmetic, and so you can make a RISC-V chip that saves silicon and saves energy, power, by not having it there. So most RISC-V systems will have integer arithmetic. You can choose to have multiplication and division. Yeah, so early retro 1980s systems don't have multiplication operations. You have to do multiplication as a series of additions, which is slow. But again, you have the choice in RISC-V if you want it included or not. You can add floating point. You can have double and quad precision floating point. Various other types of instructions. And when you buy a RISC-V chip, it will be described with a code something like this. This means RISC-V, 64-bit, and it's telling you which extensions are present. It's saying you've got integers, you've got multiplication, you've got floating point, and you've got parallel SIMD instructions. We'll talk about what those are next time. And so this spans the whole range, right? All the way from embedded through mobile, smartphones, through to desktops and supercomputers. Yeah, so anyone can instantiate RISC-V, anyone can manufacture RISC-V if they're using an open source instantiation. So here, for example, is one of the products from Sci-5. Sci-5 is making closed source implementations. Okay, so there's a lot of open source goodness in this community, but not everything is open because some of these organizations need ways of actually making some money to stay afloat. And so Sci-5 is creating closed source implementations of the open source instruction set, and they're making products like this. This is basically an Arduino replacement. It's called the Hi5. And you can buy this for about $50 or £50, roughly, to replace your Raspberry Pi. Yeah, then we also have open source implementations. Some of these are coming out of academia, especially from Berkeley. That's over in California, near Silicon Valley, where a lot of architectural research is being done. Such as Rocket. Rocket is a pipelining core. So if you're interested to go and see how pipelining actually works at the level of code over Christmas, you can go and download the designs for these. You can see exactly what is going into the digital logic design to make a pipeline. Or if you want to see the really complicated one, that's Boom. That's the one doing out of order execution, which is like pipelining on steroids, doing a whole bunch of things in parallel. Yeah, and then we have low risk in particular is doing very interesting work, taking those CPU cores and extending them with everything else you need to make a computer. So that means making the memory, the I/O, the buses, the power management, all the stuff to make a computer actually work. So they're taking one of these open source cores, the Rocket core, and they're adding all their own extra open source designs. And if this comes to fruition, it will be revolutionary. It will be the first time you can have a fully open source computer where everything is open source, right down to the transistors, right down to the sand in the silicon, for fully open source hardware computer. Okay, so we've taken a look at x86, that's the CISC side of the world. We've taken a look at RISC-V, that's the RISC side of the world. To actually connect up your study of architecture with your real-world computing, it is useful to look at how architecture links through your operating system. Most of you don't use a computer directly as bare metal anymore. We used to do that in the olden days, but almost all your computers now will be running a piece of software called an operating system that abstracts you away from the architecture. So to try and understand how the computer in your desk or in your pocket actually links to architecture, it's good to study a little bit of what goes on at that level. You do get a whole extra module on operating systems where you look at this in a lot of detail, but I just want to show you how it connects to this module here. So back in the first golden age, the 1980s, of architecture and computer design, your computer was defined by its computer design. There were different companies. You can see some of their logos here. These companies would sell you your consumer product computer. This was what you would ask for Christmas in the 1980s. You'd say, could I have a Commodore or a Sinclair or an Atari? And often these computers would share CPUs. So, for example, you get the same 6502 in the Commodore 64 as the BBC Micro. But they would wrap that CPU in a computer design. In particular, they would add different I/O devices, and they would add different libraries of subroutines in ROM, which at that time was called an operating system, although it was really just a collection of useful subroutines. And together, this defined a platform. This computer design was presented to the end-user programmer, who would then go and write games or word processors or whatever on it. But this was the level that the programmers were interested in, and it's what they wanted to buy. So you could argue whether your Commodore 64 was better than a BBC Micro because it had this certain graphics feature, it had a certain I/O device or a certain subroutine that let you do something interesting graphically when you wrote your programs. And so at this time, the computer designers and builders, they ruled the roost. They defined what these platforms were, and they created these brands which competed for end users to buy and use. So since roughly the 1990s, this has changed, and it's rare for you now to really care who makes your computer. The one exception, of course, is Apple. Okay, Apple continued working in this style, where you make a specific computer design with an entire software stack above it, and people will still go out and buy an Apple because it's an Apple. But for everybody else, they all folded into this PC architecture. You remember IBM made this deal between Intel and AMD, and they said, we'll buy all your stuff, but only if you not quite open source your stuff, but you have to at least let a second source supplier compete against you. So IBM, they went a step further than that, and they effectively opened their whole computer design. So IBM created the computer design that we call the PC, or personal computer. And unlike all the other computer builders, they said anyone can come and compete against us. Anyone can make that same computer design. And yeah, we'll lose some sales if people make our stuff, but we'll also gain sales because we'll become the standard. So IBM were the main survivor of this group of companies because of that decision. And so all the other computer designers pretty much just started making PCs that looked and felt like the IBM machine. And the end user programmers didn't really care at this point, because around 1990 this idea of running an operating system became mainstream. And so instead of booting up your computer and running a program on the CPU, you would now boot up your computer and you'd run this one program called the operating system, which could be Unix or Windows. Actually, it couldn't be Linux back then because it took a few more years for Linux to come along. But you'd run this one program, the operating system, and then that would basically hide the entire architecture. It would abstract the end user away from the particular architecture and give them a standard interface, no matter what was underneath. And so from this point, it became much less important who you bought your computer from, and it became much more important where you got your operating system from. So unless you're buying Apple, the only survivor of this style, you probably don't care very much now whether your computer is made by HP or Compaq or Dell or Samsung. Yeah. What you care about is what's the operating system. Are you running Linux on it? Are you running BSD? Or are you running something else? And so the architects had a problem at this point. It became very difficult for an architecture to distinguish itself when the operating system has abstracted all this at the end user facing. And so you've probably seen this logo. This is the Intel Inside logo. This is a very famous piece of marketing and branding. And this was created specifically to try to show the end user customer something about the underlying architecture, because this had all been abstracted away by the authors. And so Intel very consciously now try to push something inside the machine as a consumer-facing feature. So yeah, being a computer builder or computer designer used to be the prestigious part of the ecosystem, and they've really just been reduced to brands now, brands like HP and Compaq, and the components of those, you probably don't even know the names of the company that make a lot of them. Often being outsourced, offshored, especially to unbranded suppliers in Asia. So what happened when we made this change to operating systems then? The point of an operating system is that it takes over the whole computer. It's the only program that has access to everything physically inside your computer. And it's the only program that can see all the architectural features that your end user programmer used to be able to see. And so we now have this big program, the operating system. It runs in a special CPU mode. So we changed, around this time, we changed the architecture of the CPU to include this extra feature. We include a flag inside the CPU that keeps track of whose program is currently running. And if it's the operating system running, we allow it to do anything, like an old-fashioned CPU. If it's a user program that's running, we lock them out of most of the machine. And we say you can only access the machine by calling subroutines from inside the operating system. So the core program in an operating system is called the kernel. Sometimes these words are used interchangeably. Sometimes the word operating system means extra stuff as well. We're really just talking about the kernel here. The basic job of the kernel is to allow multiple user programs to run apparently at the same time. Yeah, when you run your desktop, you might have 4 different applications, and they're all in a little window, and it appears as if they're all running at once, even if you've only got one CPU in your computer. So the basic job of the kernel is to manage these multiple user programs and to give the appearance of them running simultaneously. And it does that by allowing each program to run for a short period of time by itself, and then it cuts it off. The operating system will intervene. It will say, you've had your time, stop running now. Save your state, maybe bung a load of stuff back into RAM or even onto secondary storage, and then bring in the next program and let that program run for a period of time. So if you've ever used a tool on your computer that shows you all the processes that are running, in this context the programs are called processes, you might have seen graphical tools that give you a large list of everything that's running on your computer, and often there are hundreds of processes all appearing to run at the same time. When this started, it was all done in software, and the hard part was getting control back from a user program. If the operating system runs and it says, right, it's your turn to run, you go and run your video game for a few nanoseconds, The problem is, after a few nanoseconds, the game has to give back control so that the operating system code can run again. And when this started, you had to trust the user programs to do that. The user programs had to call a special function or subroutine at this level, which would put the program on hold and give the OS a chance to come back in. That was very dangerous, because if you had any one program on your system that forgot to do that, or maybe maliciously didn't do that, then that program would completely take control of your system and would crash everything. And so the architects came along and presented a solution. So this is something else that we build into hardware at the architectural level to help operating systems go. And so the way we do this now is making use of IRQ callbacks. Remember interrupt requests? Yeah? Now, IRQ is a physical wire going into your CPU, and when you put a high voltage on it, it interrupts the program. It says stop doing whatever you're doing and just go and jump to a special subroutine that we've told you about in advance. So modern operating systems will build upon that. They'll make use of the IRQ system, then they'll extend it with the security features. So they'll give you an extra register or flag to keep track of which program is running. And periodically, usually this is just set on a timer, periodically these IRQs are triggered and they tell the operating system to come and take over. So whatever program was executing gets put away, and the operating system code comes back in, and then the OS can decide whatever it wants to do next. So there's lots of architectural innovation has gone into making this work, right? And the way that it interacts with other architectural features can be quite controversial. So if you've heard of the bugs called Meltdown and Spectra, okay, this has been described as the biggest computer security disaster of all time. And it's an architectural level bug that affects many different CPUs, including designs from all the major manufacturers over the last couple of decades. Okay? And potentially it gives you a way to break into pretty much any of those CPUs. So these bugs come from an interaction between this mechanism and some of the fancier pipelining and out-of-order execution systems that we've seen. We've seen cases where CPUs are reorganizing programs. They're changing the order they run in, and they're jumping ahead and running instructions that they don't actually know if they will get to run or not. And Meltdown and Spectre arise from that interaction. They're vulnerabilities that let you run code in this user mode. It's code that isn't supposed to be able to see the rest of your machine. But you can trick your CPU for a short period of time into thinking that it's still in operating system mode, because those mechanisms are running ahead. They're trying to do clever stuff by changing the order of execution, and it can mean part of your user code very temporarily gets privileged access. And so, for example, you can throw in instructions that will go and load stuff from a different process, like the process that is registering someone's bank account details or a password on a website. And you can load that data into your process even though you weren't supposed to, because you've temporarily got operating system level access. It's worth studying the boot process as well. So as with x86, many computers are sitting on a load of historical baggage to do with back compatibility. And the way your computer boots is often a kind of evolutionary history level. You'll see modern computers, when you turn them on, they pretend they're a machine from about 1975, and they gradually kick themselves into a mode from about 1985 and then 1995, and then they boot up into the final mode of modern 64 bits. In the olden days, again, this was very simple. When you turned on a computer, here's my BBC Micro, and there's the 6502 CPU. When you turned this on, the architecture was designed so the program counter would initialize to this address. Okay? Or rather, it would initialize to the value stored in this address. So there's this particular location right at the top of the memory map, and the first thing the CPU is set up to do is pull the numbers out of there and stick them in the program counter, right? And then you'd have other programs sat in ROM down here, and that first address is probably going to point to somewhere in ROM, and then that's the first program that runs, and then your computer's off, it's up and running. So nowadays it's more complicated, right? Your computer probably boots through a sequence of stages looking a bit like this. Because of these back compatibility requirements on x86, the computer has to start off in original x86, that's 16-bit mode. It's pretending it's a much older computer than it really is. And that's because you might potentially want to run some of your old software on it that you wrote back in those days, and which your company now relies on, and which all the people who wrote it have left, and there's no one who can upgrade it to a modern machine. So on these old x86s, they worked very similar to the BBC Micro. There was an address at the top of memory, right, and that's an address with a bunch of 16-bit Fs in it. It will pull the first address out of there and jump to that place in ROM and start executing. Now the problem is the top of 16-bit memory isn't the top of modern memory. Okay, it's actually in a really awkward place now. It's about 1 megabyte through the address space. But because of the history, that's still where your modern PC is going to boot to. So when you fill your memory, you might be putting in all your RAM modules, filling up that address space. You've got to leave this special little gap around 1 megabyte where the boot is still going to go. And so nowadays, instead of booting to a ROM operating system, you've got to put something in the ROM at that address. But normally what we put in now is a small program called a bootloader. Okay, and this can be done in ROM. In some cases, it can be done in software, and the ROM is just going to jump you there. But roughly, this is going to kick you into the sequence of modern modes. It's going to take you into 32-bit mode, then it's going to take you to 64-bit mode, and during that process, it's going to activate other parts of your architecture that were invented during those steps in its evolution. So that means activating the north bridge, the south bridge, the RAM controllers. It's looking at all the parts of the computer and setting everything up so that the CPU can actually talk to everything. So the open source version of this is called Coreboot. You can look at the source code for that and see exactly how a boot process is done. When that's finished, it's going to go and call out to another program called the BIOS, and usually this is also on ROM. Traditionally this was called PC BIOS, and this gives you the kind of early 8-bit graphics, this kind of thing that you see on some computers. More modern BIOSes use a new standard called UEFI, which looks like this, and this roughly makes your computer look like a 16-bit machine rather than an 8-bit machine, and it might let you have more colors and use your mouse. But at this point, you've got a restricted form of operating system giving you some control over I/O and peripherals, and it's usually just enough to be able to interact with the machine to set the configurations for everything else. And that's roughly the level that a 1980s or early 90s machine would actually run normal programs, such as games. Like you can write video games just running on the BIOS, okay, without having to go into an operating system. But usually the main function of the BIOS is to call another program called the OS loader, such as Grub. But here's Grub running on top of the BIOS in those low resolution graphics, and then the function of that program is to call up your operating system, such as Linux or BSD, and that gets you into all the stuff you're going to learn about next semester in your operating systems module. So again, this stack is interesting in terms of computer security. Okay, there have been several recent controversies around bootloading, such as the secure boot protocol is a way for an operating systems maker to lock down your computer so it can only ever boot that operating system. If you're ever faced with a computer that has that bug on it and you need to fix it, here's how you do it. You need to power down your UEFI chip. That means removing the battery, which is often a small coin-sized device. Or sometimes you have to reset its firmware. You might be able to find 2 pins on the chip. If you open your computer up and stick a little bit of wire between them, then you can get rid of the secure boot and go and install a better operating system. Another controversy has been this thing called Minix 3, or Intel Management Engine. Somewhere in that boot stack, allegedly, Intel have hid an entire operating system which has full access to your computer, including everything going across your network, and which could potentially be backdoored by a bunch of government agencies who could just see everything that your computer is doing. And it's built into the Intel chips at the hardware level, so very difficult to actually get information on. So that system is called Minix 3. It's an early ancestor of modern Linux, developed as an academic operating system. If those allegations are true, that would actually make Minix the world's most widespread operating system, because every single Intel CPU in the world is running it underneath their main operating system. Okay, so hopefully this helps you to link what we've studied in theoretical architecture with what's going on your desktop or in your pocket. We've studied performance, how we measure computers. That helps you to buy computers. It also helps you to design them, especially if you're doing risk design, which is very driven by these metrics. We've looked at Sysworld, meaning the long history of x86, which has many instructions, very niche, very big, very heavy, very complicated, very laden down with history. We've looked at RISC-V, which is the new lean and mean open source ISA, having a small number of simple instructions. And then finally, we've looked at how it all connects to your everyday machine through operating systems and the boot process. If you'd like to learn more about contemporary architectures, here are some links. We'll give you some optional x86 stuff in the workshops. If you'd like to learn RISC-V, I've given you a link to a RISC-V emulator. Really good stuff to do over Christmas. Right, we put this lecture here so that you can spend your Christmas holidays doing some practical assembly hacking. Please have a go in either x86 or RISC-V, and I'll see you next time for Parallel Computing.